Hi, everyone. Thanks for joining us today. My name is Julia Briette. I'm a product marketer here at TechTom, and I am joined by Joseph McAllister, who is on the ML platform team at Coinbase. So, Joe, I'm going to turn it over to you to introduce yourself, and then we'll get started.
Yeah, hi everybody, I'm Joe. Coinbase, we use machine learning for quite a few different use cases. I'd say the biggest ones would be fraud prevention as well as recommendation systems. And we also have some pretty exciting stuff around analyzing blockchain data. I sit on the ML platform team, and there's all these different users of machine learning. And so we have a common set of challenges that probably most companies like Coinbase face around shipping machine learning models to production. And that's kind of why our centralized ML platform team exists. And so our team's responsible for building out these core components. And so I think like at the very high level, the big components are going to be feature platform, model training stack, model serving infrastructure, and then also a lot of tooling around registering models, tracking experiments, and how you actually observe model performance over time. So I focus on many different areas within the ML platform, but I spend a large amount of my time working on our feature platform.
Awesome. That's a really substantial scope for your team. I'm particularly, of course, interested in the fraud detection piece since that's critical for a crypto platform like Coinbase. What are some of the technical and businesses like realities that you're facing and you're defending against in fraud detection? Like, why does speed matter so much here?
Yeah, so I think what's special about fraud prevention really in any industry is that it's an adversarial situation where the attackers and fraudsters are constantly trying to adapt and exploit gaps so that they can commit fraud. So when you look at speed, you're constantly needing to improve your systems to prevent new attack vectors. And so I think speed, like how we actually look at speed internally, there's a lot of different ways, but I think one that I am especially focused on is how quickly can we improve the model performance, ship new models, incorporating new features or new techniques. And so, yeah, Tecton's one piece that helps us ship models faster.
Yeah, that makes perfect sense. I mean, you're literally like racing against the attackers who are trying to actively break down your defenses. So I'm sure that comes with a lot of real-time requirements in different, aspects of your ML systems. Um, But speaking of like real time, I wanted to dig into the technical foundation a little bit more. What does like production grade performance actually mean for real time ML at Coinbase's scale? And what like breaks down when you're not production grade or production ready?
Yeah, so I think what's interesting about ML ops broadly is that you have all of the core requirements for a production grade system at any company that operates at scale. So we're still looking at the typical things like high availability. How does the system actually scale? We have horizontal scaling, vertical scaling. All of those things are still like the kind of classic foundational pieces for building production systems. But then when you add ML, you have a whole another suite of requirements. So we also then are orchestrating hundreds and hundreds of data pipelines, and we need to make sure those are highly reliable and that they're also meeting our freshness requirements. So that's kind of the core responsibility of a feature platform. And then also there's this kind of separate workflow that's more like a traditional microservice challenge where you're looking at just the latency. So we're trying to make some prediction and maybe we're blocking the user in the meantime. So we have like we want to make sure the app's very quick. So we have a few hundred milliseconds at most to actually enrich features, make a prediction, and return that all the way to taking the action based on the model's prediction. So I think that's why I love working in the MLOps space is that you have both just the traditional requirements, and then you also have all of these really unique requirements that only really come up when you're looking at machine learning systems.
Yeah, that makes sense. Which I'm curious, what parts of that latency, getting to that latency, are challenging? Like, is it more in the compute and like data transformation side, or like serving? Is it kind of the way that those pieces work together? Like, can you talk a little bit about what's, uh, what you need to kind of think about there?
Yeah, I think there's almost like two separate aspects. So one is on how we actually compute the features. So
Mm-hmm.
you look at the system, it's quite complex where there's data is being produced that's useful for machine learning models across dozens or maybe even hundreds of different systems. And so you need to understand how is that data being produced in the first place, and what kind of like reliability does that source of data actually have. And so then then the feature platform comes into place. And so you make all these decisions around whether you want to do batch, and if you're doing batch features, how frequently are you computing them? If you're doing streaming, do you need sub-second freshness, or are you willing to trade off cheaper compute because freshness is not as important for this use case? And so that's like one half of the picture. And then those are like all the trade-offs for just designing these features. And again, these are like hundreds of features across dozens of models. And so it gets quite complex just when we look at the offline compute portion here. And then there's all these separate set of requirements when we come to serving models. And so for any given request, we're often looking up, I guess you'd call like hundreds of different columns across dozens or hundreds of tables. And that's how we actually get the features. And so that's just one piece. We need to keep that super fast, because then we also have model inference that needs to happen. There's like a very strict budget where you have amount of time you're willing to spend for feature enrichment, amount of time you're willing to spend on the model inference. Is it running on CPUs, GPUs? And so, yeah, we talk about like real-time ML. That's kind of the constraints we're operating within.
Yeah, makes sense. Now, if we zoom in on the streaming, just the streaming piece, I know you're doing some pretty sophisticated work there. Can you walk us through your streaming architecture and like how you use Tecton and Databricks, how they work together in your pipeline?
Yeah. So again, like you go back to where's data coming from? Coinbase has many, many microservices running, and those produce different events, things that are useful for machine learning. Like a classic one is just like the user just logged in and some metadata about their login event. But there's, again, hundreds of different events. And so machine learning engineers discover these events and which ones are useful, and the services are responsible for producing them to Kafka. And so that's kind of the first step. That's upstream of the things I work on. And then downstream, like with our team, we then have many different Spark jobs consuming these events. And so there's different ways to architect those jobs. You can have stateless jobs that aren't doing any aggregations within memory, and you push the aggregations to when you're reading features for inference. You can also do Tecton support stream tiling, which allows you to do the aggregations within the Spark job and then write tiles into the online store. And so there's just a bunch of trade-offs with how you choose to design those pipelines. But yeah, at the high level, it's really like Kafka into Spark jobs that are kind of orchestrated by Tecton and doing aggregations defined by Tecton. And then those get written into an online store, where we can actually read those features at serving time.
I see, I see. Are you able to go into what those trade-offs are at all?
Yeah, for sure. There's several axes for the trade-offs. One is obviously how much compute are you willing to throw at the problem. So you can scale up clusters, and that will improve performance of things. And then doing aggregations, a stateless job is going to be the best performance you can get for any stream processing system, whether it's Spark, Flink, or anything else. And so stateless jobs are just transforming the event, filtering data, and writing directly. So that'll give you the best freshness, but then you're trading off latency at read time. And then you can also do aggregations in memory, which does introduce some freshness, like we'll get slightly less fresh features, but then you're basically setting an upper bound of how many rows you need to read from the online store. So that's kind of broadly called tiling. I think one interesting piece that Tecton has is this concept of batch compaction, which applies to both streaming and batch feature views. But the idea being basically we're doing a super long running aggregate. So we want to do like sub-second freshness for user level feature that goes all the way back to their lifetime. So like many, many years of data since Coinbase has been operating as a company. Tecton allows you to push that computation for the majority of data into a batch job. That's called the compaction job. And then just write a single tile for basically summarizing all of the data of the user's history up until 1 day ago. And then you can keep your streaming job quite simple because it really only needs to be writing tiles that aggregate over the last 24 hours. And so that part of the architecture, I think it really simplifies it because as someone building a feature, if you are sure you need a lifetime aggregate, that's really just changing a few lines. And then even though the data pipeline that actually is going to produce your feature becomes a lot more complex under the hood. Yeah, I think there's probably some details.
Yeah. I'm understanding that there's a lot that goes into stream processing, and it sounds like you've essentially, abstracted a lot of that for your MLEs. And also, I think you also mentioned that this is also like abstracted for non-engineers. Could you talk about that a little bit too, like how you're enabling, your risk analysts and other non-engineering folks to leverage this kind of really complex and sophisticated like streaming architecture?
Yeah, so that's I guess for people listening, like I am not typically building features, right? I'm working on the infrastructure side of this, and so there's a very wide set, like a range of skill sets of people building features internally at Coinbase. And I think one of the things that we've been able to unlock is the ability for people that are not very familiar with stream processing at all, maybe come from more of a data science SQL background or even just traditional software engineer, but less familiar on data pipelines. They're able to focus on, I'd say, the core logic of what they're trying to do and not be thinking about details around like things like watermarking, how many like workers am I putting in my Spark job. So like these are details that as an infrastructure team, we can worry about setting sensible defaults and tuning things. But then when I'm a user at Coinbase actually trying to build a feature, those pipelines, you're really worried about filtering and transforming the events. And then maybe we'll talk a little bit later about actually how we define the data sources and make that super easy. But you're focused on, I want these set of events, I want to filter and transform them, and then I want to run a certain set of aggregations over a certain window aggregate. So you're really defining like the semantics of what you want and declaring that versus any of the technical details around like how do we backfill this pipeline, how do we run the streaming job, are we using compaction or not? We can set really sensible defaults, and then for I'd say like particularly complex data pipelines, we're able to step in and help the ML engineer or the data scientist trying to build the feature.
Yeah, that's really cool. I definitely want to dig in a little bit more on developer experience and those kinds of extractions a little bit later too. But I wanted to, before we do that, I wanted to ask about the optimizations that you've done. You wrote a blog post about your sequence features recently. That was really awesome. And in there, one of the things I noticed is that you talked about moving to like single node Databricks clusters and how that saved on compute costs. Can you talk about like what drove that decision and the experimentation with that, and if you found any other like optimizations that have been effective for your real-time workloads?
Yes. So there's like a lot of active work here still. So I think there will be some future blog posts about some collaborations we're working on with our data platform team, but specifically on the single node one. A few optimizations we found that are really useful is one is matching the number of CPUs of the cluster to the number of Kafka partitions. And that just improves Spark performance. I'd say for people familiar with Spark, probably for pretty obvious reasons, that's useful to do. And then also on single node though, we're running one streaming job at all times for any of these different streaming feature views in Tecton. And so there's a overhead to having this driver running as a separate machine. And so by using just single node, we've basically been able to eliminate that overhead and lower the total number of CPUs or like the total size of the cluster we're needing to run without actually impacting the freshness of the pipeline or the performance characteristics at all. So that was kind of the reason for the applying that single node optimization. And then we found for like every single one of our workloads that ends up giving us the best performance and cost trade-off.
Awesome. So you're essentially like matching your compute parallelism with your data parallelism in a way.
Yeah. Yep.
Cool. Now I said since I mentioned sequence your sequence features blog, I wanted to dig in a little bit more on that. This is where you're basically like capturing patterns of user behavior, right, in a way that models can learn from. Could you walk us through like the technical architecture there and like how does an event flow from Kafka to being servable in a model prediction?
Yes. So I think the actual data flow is basically the same, where we have one or more Kafka events that are available, and we have one or more Spark streaming pipelines consuming the events. And then we're still using Tecton and Spark as like the main driver here. But there's a few different challenges with sequence features specifically. One is that you're typically you're always looking at a last aggregation. So you're looking at like the last number of things the user did. And you also maybe need to you might want to compare the current sequence of actions with historical sessions the user had. So you might have like the most recent things the user's been doing on this active session that led to whatever's triggering model inference. And then you might also want to look at the previous time they were active, look at the sequence of actions they did there as well. And so that's kind of the problem statement. I think one challenge here is just the performance of last aggregations can be challenging. And so we spent a lot of time internally and then also working with Tecton to make sure we get really excellent performance on the last aggregations. And the other piece is just when you talk about building a sequence feature, you're not looking at one event type anymore. You're potentially looking at dozens of events across even multiple topics. And so that's where one thing that can be challenging for like a data scientist or analyst trying to build a feature. And so one thing that our team did was basically introduce an abstraction where we register these events and really declare their schema, the topics they come from. And that's useful both for sequence features and just standard streaming features. But then we also we have auto-generated code so that if you want to select 4 or 5 different events, maybe they're from the same topic, maybe they're from different topics, we'll handle unifying the schema and unioning different streams from different topics into a single data source for you. So there's like a lot that goes on there when you're constructing multiple like streaming data sources and unioning completely different schemas potentially between different events into one single event that then a normal Tecton feature view, you can do any filtering and transforming you want to how you actually construct that schema. So that's what we kind of call it an ML event registry. It's really about building out the shared schemas and then being able to quickly generate data sources. And the other big piece here is any given event is used by multiple sequence features and multiple standard, like typical batch or streaming features. And so this works very useful for all of them. One person, when they find a new event that is useful for ML, they're able to just register that one time. And then everybody else in a single line of code can generate the data sources they want that mix and match any number of these events.
Wow, that's actually super impressive because like how do you handle that's a lot of like schema diversity, right? How do you handle schemas like potentially change it, like the evolution of schemas over time?
Yeah. I think there's a few pieces. One is just like even unioning the schemas is actually non-trivial. There's not great tooling to take a bunch of different Spark schemas, PySpark schemas, and unioning them together when maybe they have the same field but a different type for between different events. And now you need to take like the wider type. And so we built that out, and then we shout out an engineer on my team, Paco, who did a lot of this work. And yeah, that was non-trivial. But then also with evolution, I think Tecton actually helps a lot here, where you strictly define the schema. And so you're able to add new columns or like new pieces within the schema if you need to, but that's an explicit action. And then Tecton also alerts you to when you're generating this like Tecton plan that shows you the diff of the changes you're going to apply. That shows you that you're adding new schemas. These downstream feature views are impacted. You have the option to basically rerun all the backfills if you want to, or if it's kind of like a change that's fine to make in place. Maybe the new field was just emitted and you just want it for features going forward, but it'll be null in the past. Tecton gives you the option to basically make that call. I think, yeah, in reality, like we need, these schemas are often extremely complex, and we need a few fields or a dozen or so fields within the event that are actually useful for our purposes. So I think that the schema evolution hasn't been as much of a challenge. And then we've solved the problem of like schema unionization, combining different diverse schemas.
Okay, yeah. So that was like the core piece that you needed to solve for. That makes sense. Now I'm really curious about like how you're using Tecton's continuous mode. You mentioned that you use it with like 0-second micro batches, and you mentioned also before that these jobs are stateless; they just consume and transform right to DynamoDB. Can you just expand on that a little bit, just for folks who may not be as familiar with what that means?
Yeah, so as of June 2025, like Spark streaming is running in this like short micro batch. Is how you get the best performance with Spark. And so for like ultra latency sensitive use cases, we're able to just run stateless jobs. And if you just need the last aggregation, you're just upgrading like the last single event of that type. You're just writing to the online store, and it's just one record that you need to read at serving time. And then there's also other trade-offs. You can do aggregations, and then read time latency can change, or you can use stream tiling, which still gives strong performance. And that way you're writing maybe like a 1 hour tile. And so if you're only aggregating over 24 hours with batch compaction, you're limited to just reading 24 rows from the online store. Yeah, and then I guess I kind of alluded to it, but there is a major change that was recently announced, which is Spark. There's also a Spark improvement plan that covers it in detail. That's pretty interesting. But they're releasing this thing called real-time mode, and that basically the idea is you have long-running micro batches, but then you're processing data continuously. And so I think that can even bring down or improve the freshness, reduce the pipeline latency significantly. So we're actively working on that as well.
Cool. Yeah, have to keep an eye on that. I guess the follow-up question on that is like, how does this differ from what you would build with just like raw Spark and Flink?
Yeah, so like we're running, like we use those tools already. So you definitely can build these things with them, but then where Tecton adds a lot of stuff on top is really around the tiling and compaction. I guess there's two pieces. One is the developer experience, where you're really the DSL makes it so that you're focusing on filter, transform, and the aggregations you want. And then all the other details are kind of abstracted away. So that's one piece would be not something you're going to get with like vanilla Spark at all. Or
the manual work involved.
Yeah. That's you're not provisioning infrastructure for a specific job. Like that's where this kind of declarative approach lets you see what jobs and backfills are going to be run, and is really powerful. And then there's the actual performance optimizations, which we've talked a good amount about, and that's where you're getting the great performance because you're not just running one streaming job and then maybe you're limited in the amount of like a look back window that you can support because there's so many events in your memory and checkpointing becomes a challenge. But you're leveraging compaction and tiling so that you're able to reduce the overhead of computing these features, but you can use any look back window you want. So I think that's where, yeah, Tecton comes in because it just makes these like single lines of configuration when you write the feature, and then we have very common set of workloads now, and so we can just have all these different unit tests and things to prevent someone from writing a really inefficient feature. You can set really good defaults for people.
I think that's a great segue actually to go back to developer experience a little bit. What is it? Can you just tell me like what it looks like day to day for an ML engineer or someone on the ML use case team to build a new feature?
Yeah, so I think there's a lot of upfront work and domain expertise to know like what data is available and are we using it already or is this new data? So there's definitely a piece that comes in even before the like ML platform is there, and that's just pure exploration of the data that's available. And so you might be using like Databricks or Snowflake, just like a typical tool for exploring this data. But then once you have an idea for a feature, you have some sense there's a table that I want to use or there's an event I want to use. That's where we come in. And I think what's really great about it is from the very beginning, you're working with the production data. So you're in a notebook environment and you're defining the data source, which is typically only a few lines of code. And then you can immediately start to define the semantics of your feature, which is like, and basically build it out. And so that's really a very rapid development workflow. And then I think what's even more powerful is, let's say you have your model, you know the performance, you've already trained it, and now you're trying to improve it. So naturally, one thing you want to do is add a few features. And what we can do is take your existing training data set and append on several features so that you now have new, like you build new pipelines in your notebook and you're now adding them to your training data set. And you don't need a PR review. You don't need to like copy your code into like Git or anything. It's just something you can do and iterate on. And then if you want to do some really large workload, we have tools that also let you trigger like very large jobs. But for many of the Emily workflow, they're looking at like a sample of their data set and they can get really good performance just with defining these things, iterating on them, seeing if the performance is good. If it's not, trying new data sources or different aggregations. And so like that feedback loop is something that we care a lot about. And that's where I think we're doing a pretty good job right now, where you can iterate really quickly. And that's just the area that our team's constantly pushing to improving even more.
That's awesome. Yeah, I love the like proactive approach of surfacing those like relevant features and automatically like including the training pipelines is really smart. Now I want to talk about the like kind of classic, one of the classic like ML infrastructure challenges of backfilling. How do you handle this? What did this process look like? Before you had Tecton, and also like how long do backfills typically take now?
Yeah. When you define your feature, so I guess we actually kind of skipped over the productionization part, but you build this feature in a notebook, and then at some point it's like, okay, I have evidence that this is going to be useful for at least one model, maybe more. I need to actually ship that feature. And so just jumping back, like at that point, you are creating a pull request, and there is a review process. We have SLAs for like how quickly we'll review features, and you can see exactly what's going to happen when you create that pull request with your new, like one or more new features. And so as part of that, there is no concept of like a manual backfill or having to take any additional steps. When you declare the feature, Tecton is able to calculate how many jobs it needs to run. You have some knobs you can tune to say basically, I need to backfill 2 years of data for this feature. I want to run many parallel jobs to make it faster. How many like weeks or days or months of data do I want to process for that backfill, for each backfill job? And then Tecton has basically handles all of that for you, where it's going to trigger, I think it's like defaults like up to 10 jobs in parallel to run these backfills. And then you can see the progress. It'll also alert you to anomalies if, say, you're using some data, and when you were testing with your recent like few months of data, it was super useful. And then you just try to backfill it now for 2 years. If maybe that event wasn't produced, it's some new vendor we're using, or it's a new service that produces that event. Tecton has the monitoring to basically give you an alert saying, hey, for this backfill range from 2024 January into like the end of or the beginning of 2025, we actually had no data for this. So maybe that's okay, and that it's a new event you want to use, but it's really useful to know that. Or there also could be an issue that this helps surface. And then, yeah, you basically merge the PR, the backfills are triggered in parallel. Tecton lets you know if something went wrong, but since you're working with production data in the notebook, that's not a common occurrence at all. Like if you've tested in your notebook, you have very high confidence. And then Tecton also has validation checks that just make sure, like sanity check things, that like schemas match and the input output is all typed correctly. I think that's one thing that was really great. I think before Tecton, we were working with a lot of YAML files, which is probably, I imagine there's some people listening that also are in kind of a similar situation to that. And I think the Python DSL and like really strong validation that actually runs against like real schemas, not just what's defined in the code or the YAML file in the old world. That's definitely improved the process to where I think about backfill performance, but the people building features don't really consider that. They just know their data will be ready when they need it.
Yeah, I know that's a big deal. And like being able to kind of see, one, getting those alerts, and two, like sort of being able to do a little bit of like planning before you like execute backfill. That's cool to hear about. Now, before we wrap up, I just wanted to see from like your perspective for maybe other like people who are building ML platforms, or just anybody working on these similar use cases. What are like in your opinion, like any big technical like pitfalls to avoid, or just maybe not so much like where to avoid, but where to focus your efforts on first?
Yeah, I think probably the easiest piece to not focus on, but it's a huge detriment if you fall into that trap, is the observability piece of things. And so there's defining pipelines, and you can make that super easy, and then shipping them and ensuring they're always running. So there's just like basic reliability of the pipelines. But then once you reach where we're at with thousands and thousands of features, how do we ensure that not only are the pipelines running and there aren't issues there and they're like efficient and we're not spending unnecessary amounts on the compute, but then are the features drifting? If they are, it can be tough to see if it's a like natural change, like a concept drift, or if it's something actually wrong. There's like something wrong either with our pipeline that changed, or upstream, maybe the meaning of the event has changed, and they may or may not know how strong of a dependency our models have. And then even within that, there's also some models might use thousands of features, and so it's important to have the priority list of which are the most critical features. There's different methods to quantifying that, and ensuring those are particularly high quality. So I think we invest a lot as one of the places that our team can have a lot of leverage, and we want to expand what we can offer. And so, yeah, I'd say observability there would be the like biggest potential pitfall, and it's kind of for, I guess, what's obvious reasons for everybody working in ML. That's like observability is mission critical for the quality of the performance. Without data, they're completely useless. So yeah, I think it's like something you have to tackle holistically. And there's also observability on like the online serving path, like all the typical P99 latency, error rate. Those are all things you have to track. But then I think the really challenging part is the data observability. And that's something that spans not just the feature pipelines and feature serving, but also goes all the way up into the like far end of the stack closest to the customer and the services they're interacting with.
Yeah, totally. Don't overlook data observability. Got it. Well, Joe, this has been amazing. Thank you so much for taking the time and walking us through. I know at Tecton we are so excited about the work that you're doing, and everything that you described is just speaks to like such technical innovation and like practical engineering best practices that I think a lot of folks can learn from. So thanks for walking us through it.
Of course.
Cool. All right. Have a great day, everyone.